is 5:30. This one is also optional, so I'm going to go ahead and get started. I will have the chat window open as well as the participant window, so I'll know who's here, and then I'll also be able to see the chats. I'm going to go ahead and just start off by sharing my iPad screen with you. I've already asked everybody if they had any questions, but I'll ask one more time just in case. Anybody have any questions about any homeworks or anything before we get started? Now, I also want to remind everybody, I sent everybody out a text message just to make sure I didn't forget to do it. But I sent everybody out, actually not a text message, I sent them out an email reminding you that our first online test, not our first face-to-face, but our first online test, is due this weekend. For your class, the one that's meeting right now, the PHY 2420005B, their test is due, if I remember correctly, it's Monday night, so that would be like February 2nd at 11:59 p.m. Whereas all my other classes, theirs is due at 11:59 p.m. on Sunday, which I think is February 1st. So keep in mind that the practice test will disappear at the same time. So the whole purpose of the practice test and the reason I give you extra credit is trying to compel you to make sure you take it a bunch of times because it's the single best way you can prepare for the test. And it's just like the way I used to do it as a student myself. How I got fairly decent at physics was by working a lot more physics problems than the instructor would actually assign. And it was mostly a matter of, I look at a problem and I can't figure it out, so I try to find one like it. I figure that one out, and then try to see if I can apply that to the problem I'm working. If not, go look for another one, so on and so forth. So it's a true tried and true way. It will work, but I just want to make sure you guys sort of go through that process. A lot of what I see when I run into students, whether they be my own daughters or son, well, I have a nephew who's sort of like my son right now. He's living with me, and we're sort of raising him, putting him through middle school and high school. But they're like my kids, so when I find they're having difficulties in math, it's almost always due to just not having enough practice. And then the second thing is they didn't understand sort of the big picture, and I see that a lot. It's a lot of times you just have teachers that aren't necessarily teaching exactly why they're doing what they're doing. Or at least the students aren't getting it. It could very well be that the teachers are saying everything right and the students just aren't getting it. But practice makes perfect. I'm going to go ahead and start up then, since it doesn't seem anybody has any questions. I'm going to start off with example 19.5 from your textbook, and it's called Unknown Specific Heat Determined by Calorimetry. So this is example 19.5, and let me read it to you. Again, if you have your book available, it's much better to actually open to that page, at least in the ebook, and so you can read the question if you have it. Uh, if you have it open, that is. So the question is unknown specific heat determined by calorimetry. An engineer wishes to determine the specific heat of a new metal alloy. A 0.150 kilogram sample of the alloy is heated to 540 degrees Celsius. It is then quickly placed in 0.400 kilograms of water at 10.0 degrees Celsius, which is contained in a 0.200 kilogram aluminum calorimeter cup. The final temperature of the system is 30.5. Calculate the specific heat of the alloy. So I'm going to write down what information I gleaned from that. And it says an engineer wishes to determine the specific heat of a new metal alloy. And the last sentence says calculate the specific heat of the alloy. So I'm going to say C question mark is equal to question mark. And actually, I won't even subscript it question mark because that's actually a pain in the butt to write. I'm just going to say C. I don't want to, I'll say CU for unknown. So that's what we want to know. What we know is the mass of the sample, MU, is equal to 0.150 kilograms, and T0 is actually 540 degrees Celsius. I know that it's T0, and by the way, I'm going to assume that's 3 sig figs, so I'm just going to put a dot here and a zero with a underscore so that everybody realizes that the zero is not a sig fig. I know it's a T0 because what's going to happen is you're putting that in water, it's going to cool down, so the final temperature will be much lower. It is then quickly placed into 0.400 kilograms of water, so I'm going to say M water is equal to 0.400 kilograms. I happen to know the specific heat of water is 1.00 kilocalories per kilogram Celsius degree. And I know its initial temperature is 10 degrees Celsius, so that's T0 water is equal to 10.0 degrees Celsius. And I also know it's this water is contained in an aluminum cup, so the mass of the aluminum, which I'll just call M sub Al, is 0.200 kilograms. The specific heat of aluminum, I happen to know, is 0.22, and that's also in kcalories per kilogram Celsius degree. And its temperature, we're assuming basically that it also had the been in equilibrium with the water that was in it. So it too has an initial temperature of 10.0 degrees Celsius. And the final temperature for all of these is T final is equal to 30.5 degrees Celsius. So that's the information that we need. Again, there's two ways we can solve this, or two major ways we can do it. And one is taking the summation of the Q's is equal to zero. So that would be summation of the Q's equals zero. I don't generally even try to teach that, not because it's, impossible or it's wrong or anything like that. It's actually very doable, and you might find it more helpful. It's just I find that a lot of times my students complain when I give them more than one way to do things. So I've just parted with that, knowing that this way doesn't help very much. But if you wish to do it that way, your author takes the time in a couple of problems of getting you to do it using the delta Q way for his example so you can see it. But the main thing is when you're doing the delta Q equals zero way, or excuse me, I said delta Q. It's supposed to be the sum of the Q's. I don't know why I wrote delta there. Okay. It's the summation of the Q's. When you use the summation of the Q way, you have to be very persnickety. For instance, every time you use the formula Q equals MC delta T, each of those delta T's have to be put in final minus initial order. So it's got to be final minus initial order, or else everything gets messed up. So that means some of your terms are going to be negative, some of your terms are going to be positive, that sort of thing. Not only that, when we get to the next section, that covers latent heat. That inherently has a sign depending on if you're going, for instance, from steam to water, or excuse me, from gas to liquid. Then there's one sign, and if you go from liquid to gas, there's another sign. Then there's a different value altogether if you're going from liquid to solid, in which case, again, you have another value, but it has a positive sign in one direction, it has a negative sign in the other direction. And I've just discovered that in the heat of a test, it's really easy to forget what those signs are. So by doing it the other way, which is Q lost equals Q gained, you make sure all the terms are positive, and it just works itself out a lot easier. So I'm going to go with that second way. That second way is Q lost equals Q gained. And these problems are called calorimetry problems, and that's because in general they are done in a calorimeter, which is more or less like a cooler. You're thinking of it as a cooler, but the way the calorimeter is normally set up, like the ones we use in our classroom and our labs, is we have a big aluminum beaker, and that aluminum beaker has sort of a little wall that as you go from the top, it goes in a little bit and then goes straight down, hits the bottom. comes back up, goes out a little bit, and it has that little shelf on the inside. Well, that little shelf is where you put an O-ring in there. It's a big cardboard O-ring. The inner diameter, because it's an O-ring, so it actually has a circular hole and it's a circle, but the inner diameter is a little bit bigger than the diameter of the small beaker that you put inside of it. But the small beaker has a little lip that hangs off this way and that way and that way and this way. So you can sit it in there, and the only thing that's connecting that small beaker, which is like the 0.20 kilogram one we have here, the only thing connecting it to the big beaker is that little piece of cardboard. And that cardboard is only about that thick, and then it goes all the way around the circumference of the inner beaker. So the total area through which heat could flow is only like this thick plus times the diameter. It makes a rectangle, but it's such a small area and it's such an insulative material that you lose very little heat. And because it's an O-ring that's significant in size, it keeps the inner aluminum beaker from touching the outer aluminum beaker, and it basically makes a little volume of air that can't really move up and down. So it gets rid of convection. Uh, in addition to it's obviously getting rid of conduction and convection. That all you can affect it with then is radiation. And then inside of that cup, you have something to stir it. You have a thermometer that can measure the temperature, and you can have a lid. However, we get pretty good results even without using the lid. So let's get started doing this. In this scenario, the only thing that's going to be losing heat is the unknown sample. So I'm going to put that over on the left by itself. We're going to remember that the equations we're using, of course, is Q is equal to MC delta T. But in this case, since we're using Q loss equals Q gain, I got to make sure all my terms are positive. So I don't do delta meaning final minus initial, not with these types of problems. So here's my numbers for the unknown. I'm going to say 0.150. I'm going to leave the units off. You can sort of work them out in your head as we go. That would be 150 kilograms. I'm going to multiply that by specific heat, which is what we're wanting to find, but that's kilocalories per kilogram per Celsius degree. So when I multiply it by this, we're left with kilocalories per Celsius degree. And then we multiply that by the change in temperature. And as I said, we want it positive, and obviously 540 is way bigger than 30.5. So I'm going to write 540 degrees Celsius minus 30.5 degrees. Oh, I don't know why I wrote the units on there. I just finished telling you I wouldn't write the units, and I need the space. So that's 540 minus 30.5. And that's the whole thing for the thing losing heat, because that's the unknown. It's not changing state. If it was changing state, we'd also have a ML term, but we haven't even learned about that yet. So we've got this quantity. Now, what is gaining heat is the water inside the aluminum cup and the aluminum cup itself. So I'm going to sit on the right hand side, and I'm going to write down the mass of the water because that's going to be the bigger thing, and that's 0.400. The specific heat of the water is 1.00, and then the change in temperature, in this case, it's going to go from 10 degrees Celsius to 30.5, so I put the 30.5 first minus 10.0. And actually, since we're actually doing that for both the aluminum cup and the water, I'm going to save the delta T term uh, for the end just to save work, to save space on this notebook here. So there's my 0.4. I'm going to put this in. Oh, I got to put that in parentheses. Now I've got parentheses and square brackets around it so that we can better see what's going on, but also so that I can factor out the change in temperature that's going to be the same for both the aluminum and the water. So here's the mass of the water, 0.400 times the specific heat of water. Now I'm going to do the mass of the aluminum, which is 0.200 times the specific heat of aluminum. And I'm just going to double check, and I'm looking at my ebook right now and make sure I'm remembering off the top of my head the proper aluminum. 0.22 is what I said, and that is right. just it's a bummer when you accidentally copy the wrong number and you end up getting it, and it shakes the student's confidence and that sort of stuff. So 0.22 is the specific heat, and then of course the temperatures that we had were 30.5 minus 10.0. So that's going to be multiplied by everything. We can go ahead and distribute through this multiplication. For instance, I'm going to take the 0.150 and multiply it by the 540, or actually, I'll do 540 minus 30.5, and then I'm going to multiply that by the 0.150. So 540 minus 30.5 is equal to 509.5. And then 509.5, actually, let me write that down just in case anybody needs to double check it. 509.5. Now I'm going to multiply that by 0.125, or excuse me, 150, and that gives me 76.425. Oops, let me go back to blue. Going back to my blue. 76.425. Now, in this case, we actually only had three sig figs from subtraction because only one of those numbers was down to the tenths place. So when I multiplied 509.5 by 0.150, that's three sig figs times three sig figs. So that means the two and the five are not sig figs, but they are being multiplied by C sub u, where C sub u is the specific heat of the unknown. That's the thing we want to know. Now, remember, what we have here is the 76.425 actually has units of kilograms times Celsius degree. So that's just so you'll know. Now, what I'm going to do is work out the other side. I know the zero point 0.4 times 1 is 0.4. The 0.2 times 0.22 is going to be 0.044. So I can go ahead and do those. That's going to be 0.400 plus 0, zero point 0.2 times 0.22 is, as I said, 0.044. Now, in that case, I actually have two sig figs, so all the sig figs here are all the digits that I've shown are sig figs. And then 30.5 minus 10 is 20.5. And that's the proper number of sig figs. So now I can write 76.425 times the specific heat of the unknown is equal to, now I'm going to take the zero point 0.4 plus 0.044 gives me 0.444 times 20.5, and that gives me 9.102. I should only have three sig figs, so that 2 is not significant. Now I can divide both sides by 76.425. And here's the case where it might be useful for me to remind you what the units were. Okay, the 76.425 had units of kilograms, Celsius degree, and the units of the 9.102, which is this whole thing on the right, is just kilocalories. So we're actually getting, as a result of this, the specific heat of the unknown, C sub U, will actually come out in kilocalories per kilogram Celsius degree. So that's going to be 9.102 divided by 76.425. And that gives me 0.1191 kilocalories per kilogram Celsius degree. And that's the answer. Now, you could go ahead and convert that to kilojoules per kilogram Celsius degree if you wanted, but there's really no need to, as long as you have a number. On our test, I'll either have it as a multiple choice, in which case you would just have to find the units that the multiple choice answers have, or if I don't have it as multiple choice, then I'll either have to specify whether I want it in kilocalories or kilojoules or joules or calories or whatever. Okay. And of course, the other units would be there too. Anybody have any questions on that one? Okay, and looking at the textbook version of that problem, they got that the unknown was 497 joules per kilogram Celsius degree. So that's supposed to be able to be multiplied by 4,138, 4.183. So it's 4,000, 4.183. Let me double check that number. I hate it. I hate that I forget that. Or that I just forgot that all of a sudden. But anyways, yeah, if you multiply that by 0.11, you do get the 476. Any questions? All right, here's the single most important diagram for these for four chapters in my estimation. So I'm going to stop sharing my iPad screen for a second, and I'm going to share my TV screen or my computer screen specifically because of this graph right here. This is a graph of temperature in degrees Celsius versus heat added in kilocalories, and it's really basically what happens to 1 kilogram of water. So we have 1 kilogram of water that initially starts off in the solid state as ice at negative 40 degrees Celsius. Okay, so as you add heat, according to the equation Q equals mc delta T, the temperature will change. So we have Q is equal to mc delta T, and for ice, which is water, but it's different in the solid state than it is in the gaseous state, and it's also different in the liquid state. So the specific heat for ice is actually about 0.50 calories per gram Celsius degree, and that's supposed to be a regular calorie, not a kcal. But that also could be 0.50 kcals per kilogram. So if you're talking about 1 kilogram, then the M is 1, the C is zero point 0.5, and the delta T in going from negative 40 to 0 is basically 40. So if you multiply 40 times zero point 0.5 times 1, you get 20. And that's why you see right here 20 kcals have been added in bringing the ice up from negative 40 degrees Celsius to 0 degrees Celsius. But here's the part that students don't necessarily get. But this is the whole reason why, one, we can store things in freezers because they're going to hold that specific temperature or even get lower for an extended period of time. And even if you lose electricity that's keeping them cool, they'll stay in that solid state until an appreciable amount of energy has impacted them because it has to fight the latent heat of fusion to do it. So what happens is once you reach that 20 kilocalories, the water temperature doesn't change anymore. It just stays at zero, stays at zero, stays at zero until you add what turns out the latent to be the latent heat of fusion, which is going to be 79.7 kilocalories per kilogram. Okay. So once you add 79.7 additional kilocalories of energy, of heat to the water that was ice, it will finally become ice. I mean, become water from the ice state. That you can picture as it's called latent heat, but you can picture it as sort of the energy that's stored up from the atoms being in that sort of lattice structure. You know, each atom is a very specific distance away from the other atom in a very specific sort of regular pattern that we call a lattice. And in order to break that, you not only have to bring the temperature up to 0 degrees Celsius, but then you've got to break those individual bonds so that adjacent molecules are have so much energy that they break loose of their adjacent molecule. That's what that latent heat is. You've got to put in an additional 79.7 kilocalories per kilogram, which in this case it's 1 kilogram, so it's just an additional 79.7. So really, this should be more like 99.7 instead of 100, which is really close enough. At that point, you still start adding heat to the water, which now is a liquid. And of course, the specific heat of water as a liquid is 1.00 calories per gram Celsius degree. That's probably the one figure I sort of expect you guys to memorize. One of them, the 22.4 liters is another one, but this is one of them. That being said, the this 1 calorie per gram is going to be on your information, or I'll give it to you in a question. If you get on a question in a test, for instance, and you don't know the specific heat of water, go ahead and ask me. But I really want you guys to commit that one to memory, at least in calories, and then you can convert it or you can convert it to joules. So, with this in mind, we have to bring the water up from 0 degrees Celsius to 100 degrees Celsius, and that takes a 1 calorie per gram per Celsius degree, or since it's a whole kilogram, that's going to be 1 kilocalorie per kilogram Celsius degree. So, in order for us to bring a whole kilogram of it up from 100 degrees Celsius, or up from 0 to 100 degrees Celsius, I have to take what's already been added, which was 100 kilocalories, and I have to add another 100 kilocalories to it, because that's what you get when you multiply 1 kilogram times 1 kilocalorie per kilogram per Celsius degree times 100. So that's why this number right here is 200, because it took a whole 100 kilocalories to bring the water all up to 100 degrees. Now, this is the reason why you often boil things when you're cooking them. Specifically, you could always use that to cook meat. It wouldn't necessarily be good. I mean, it wouldn't necessarily taste good, but that's the origins of like the sous vide and stuff like that that's used in some restaurants, and some people use in their homes. But the whole point is, once you bring water or pretty much any liquid up to the verge of boiling, in other words, converting from liquid to gas, it stays that temperature until all of the water is actually boiled away. And what's going on there is you're slowly adding more and more energy until you get up to the 539 kilocalories that are required per kilogram of mass. So in this case, again, we have to add another 539 kilocalories per kilogram, and that's the latent heat of vaporization, which we normally indicate with a L sub V. And as I said, that's 539 kilocalories per kilogram. So that's what this pink area is us adding 539 kilocalories to that 1 kilogram of water. And finally, the water becomes steam. And then we have to raise the temperature of water even further if we wish. And when we do that, the specific heat of steam is actually not 1 either, but it's also not zero point 0.5. It's closer to 0.48 calories per gram Celsius degree. So again, in this case, you're trying to break up adjacent bonds. Remember what I told you about the atomic theory of matter was that basically the atoms or molecules are in a lattice when they're in solid state, and they're just sort of vibrating like this. But if we add enough temperature to bring it up to the boiling point, then all we have to do, or excuse me, to bring it up to the melting point, then all we have to do is add a latent heat of fusion to break it apart. To do that, you've got to basically make this move so much that it breaks this bond and this bond between these two adjacent molecules. Well, when you get into the liquid state, you still have those molecules, but now they're not in a rigid lattice. They're just mostly like for on the order of, let's say, milliseconds, maybe even microseconds. It might be as small as microseconds. A single atom will pretty much spend its time near a single other atom like this, or a molecule. But then after, an eternity at the microscopic level, which might be a microsecond or it might be a millisecond, either one's a long period of time at the micro scale, this one might move on and become a closest neighbor to another molecule, and it might move on after another micro or millisecond and so on and so forth. But still, it has a proximity to adjacent molecules at any one time, and if you give it enough energy to break that bond between those adjacent molecules, then it can go ahead and turn to steam, and that's what this bonding is here. This is the heat of vaporization. Of course, there's also a latent heat speed of sublimation. As you guys know, CO2 goes straight from the solid state, at least at 1 atmosphere of pressure like we deal with here on Earth. It goes straight from the solid state to the gaseous state when you add enough heat for sublimation. Water can be forced to sublimate. In fact, we know for a fact if you just took a pot of water and stuck it on the surface of Mars, the atmospheric pressure is like on the order of point zero. It's either 0.006 or zero point zero 0.06 atmosphere. So it's a very low pressure, and because of that low pressure, water would basically boil, even though the temperature is nowhere near the boiling point. It's just going to sublimate. So it literally would jump straight from the solid state to the liquid state if you had it there, or excuse me, from the solid state to the gaseous state if you had it there. But you could put the liquid in there, and then it would just jump straight to the gaseous state. So this diagram hopefully helps you understand that the new equation we need is Q is equal to M times L for a change of state. And that means we have to use that. If we use the summation of the Q's equals zero, we have to know whether that's a positive or a negative. If you're going from a liquid, or excuse me, from a solid to liquid, then the heat has to be added, so it's a positive. And if you're going from a liquid to a solid, the heat has to be taken away, so it's a negative. And the same thing at the top, if you're going from a liquid to steam, then the heat has to be added, or liquid to gas, then the heat has to be added. If you're going from a gas to a liquid, then heat has to be taken away. And of course, heat added means a positive Q, and heat taken away means a negative Q. So again, that's the whole reason that I tend to not use the summation of the Q's is equal to zero. It might cause some problems on the front end because you got to think about making sure you do big temperature minus small temperature instead of final minus initial. Now, in table 19.2 here, you can see they give you not only the heat of fusion and heat of vaporization for several things, they also give you the relevant melting point and boiling point, and these are at basically 1 atmosphere. As you saw in the phase diagrams earlier in the chapters we were talking about, in the phase diagrams, we found out that different pressures cause different boiling points, and you'd probably guess that that also means different melting points, and you'd be right. Any questions on that before we move along? All right, so let's look into example 19.6. So example 19.6 is what we're solving now. And I'll read it to you while we have it here, and then I'll go ahead and write down stuff and give you the iPad view again. But example 19.6, making ice. How much energy does a freezer have to remove from 1.5 kilograms of water at 20 degrees Celsius to make ice at negative 12? So that's the question. Now I'm going to go ahead and share my iPad screen so we can work it out. And I got to remember to open the chat up in case someone tries to type a message to me in real time. This should come up any minute now. Okay, now let me go get the chat box. Okay, so the chat box up now. All right, so as I said, how much energy does a freezer need to remove from 1.5 kilograms of water at 20 degrees Celsius to make ice at negative 12 degrees Celsius? So that's what we want to know. We want to know Q equals question mark. So I'm just going to, calculate the two Q's, knowing that we're actually having to steal energy from it. So technically they should all be negative, but we're just calculating the magnitude. So I'm going to say solution. We need to use Q is equal to MC delta T to make the water change temperature. And we need Q equals MC delta T. Well, in this case, yeah, we got to use water to change temperature. Then we got to use Q equals ML to account for the latent heat required. And then we've got to use Q equals MC delta T again to change the temperature of the ice. So that's our job that we're going to do. So first off, I'm going to talk about taking the water from 20 degrees Celsius down to 0 degrees Celsius. So in this case, it's 1.5. Again, I'll leave off the units just to save space, but you know it's a kilogram. I know the specific heat of water is 1.00 kilocalories per kilogram Celsius degree. And then that temperature change, I want it to be positive, so I'm going to say 20 zero point zero degrees Celsius minus 0.0 degrees Celsius. And again, I wrote the units even though I said I wasn't going to. Now, in addition to that, I have to take even more heat away because I have to add enough heat to, or take enough heat away where the atoms and molecules can actually separate from their nearest neighbor and try to form a lattice. So, in doing that, I'm going to have 1.5 for the mass times the latent heat for water, and we learned the latent heat from water in going in terms of fusion was 79.7. And I want to double check to make sure that's kilocalories per kilogram. And yes, that is kilocalories per kilogram, just double checking. And now I need to bring the ice temperature down to negative 12. So again, it's 1.5 times the specific heat of ice. As I showed you earlier, that's closer to 0.50. And now this time I need again the temperature change to be a positive quantity. So I'm going to do 0 minus negative 12. And I'll leave the units off there, as I was supposed to do on the other one. So now I can just do 1.5 times 1 times 20, which is obviously 30 kcalories, and then 1.5 times 79.7, which is obviously 119.6. We only have two sig figs though, so there's really not much need in doing more than that. And that's also in kcals. And now I've got to do 1.5 times zero point 0.5 times 12, and that gives me 9. So I'm going to take the 9 and add to it the 119.55 and add to that the 30, and that gives me about 158.6 kilocalories, but technically we were only good to the tens place, so we'd have to call this roughly 160, and that's not a sig fig, 160 kcal. Any questions on that? Let's see if I did that. No, I did do that one. I did not do this one. I'm trying to double check, make sure I got the right answer here. Oop, missed it. Missed it there. Where is it at? This is probably 19.6. No wonder I was looking at 19.7. So yeah, they're saying that 660 kilojoules, uh, and that does give me right at 158. So that seems right to me. Any questions on that? All right, let's try another one. So that was 19.6. Let's try let me see. 19 Yeah, I'm going to do 19.7. It says 19.7 estimate with all will all the ice melt. So a at a party, a 0.50 kilogram chunk of ice at negative 10 degrees Celsius is placed in 3 kilograms of iced tea at 20 degrees Celsius. At what temperature and in what phase will the final mixture be? The tea can be considered as water, ignore any heat loss to the surroundings, including the container. Okay, so this is a problem where we're not exactly sure what could happen here. We know that putting the ice in the tea is going to rob some of the heat from the tea. And that's sort of the whole purpose of it because iced tea is supposed to be roughly 0 degrees Celsius, so that it's on the verge of freezing and then it's very, very cold. But that's what's going to happen. Now, the big question is the block of ice big enough and cold enough where the heat required to melt it is larger than the heat required to be pulled away from the tea to cause it to freeze? Or is it just enough to bring it down to zero? Or is it just enough to bring it down to a temperature other than zero, but close to zero? All of those are options. So, what we're going to do in this case is we're going to write down what we know. And we know, for instance, the mass of the ice. This is example 19.7. We know the mass of the ice is equal to 0.50 kilograms. We know the temperature of the ice is equal to negative 10 degrees Celsius, which I'm going to write it like this so we can see at least has two sig figs. And the T, which we're going to treat as water, so I'll just use a W. The mass of the water, which is T, is 3.0 kilograms, and the initial temperature of it is positive 20 degrees Celsius. And what we want to know is T final equals question mark. But we really want to know more than that. We want to know what the state of it is and all that good stuff. So I'm going to start off with solution. Obviously, the equations we're using are the same ones we had before. Q equals MC delta T, Q equals ML. And we're going to use the fact that the specific heat of ice is equal to 0.50 kcal per kilogram, and the specific heat of water slash T is 1.00 kcal per kilogram Celsius degree. And that should do it. Oh, we also need the heat of vaporization, or excuse me, the heat of fusion for ice. And that is L fusion ice is equal to 79.7 kcal per kilogram. So, first off, let's calculate what it takes to actually completely melt the ice. So, Q melt is equal to the mass of the ice, which is 0.50. And what I'll do is I'll do the temperature change first. So I'm not going to call that melt. I think I'll call this bring to zero or something like that. So I'll say Q to zero. That's going to be the mass of the ice, 0.50, times the specific heat of the ice, which is 0.50, times, in this case, we're going to, again, just treat everything as positive. So I know that I'm changing from from negative 10 to 0, so the change in temperature would be 10 Celsius degrees, like that. So just that quantity alone gives me zero point 0.5 times zero point 0.5, which is the same thing as 5 times 5 is 25 over 100, so it's 0.25. And then I multiply that by 10, that gives me 2.5 kilocalorie. Okay, so that's what it takes just to bring the ice down to 0 degrees. Now to melt it, that's going to be just M times L. So that's 0.50 times 79.7. And of course, half of 79.7 is equal to 39.85 kcal. Now, we only had two sig figs, so these two are not sig figs. But you can see right now that basically to bring the water down to 0 and melt it is going to require about, you might as well say, what, 43 kilocalories, somewhere around there. Now, what we also want to know is how many calories or kilocalories does it take to bring the entire vat of tea down from 20 degrees Celsius to zero. So let's say, calculate that. So T to zero, well, T to 0 degrees is going to be 3.0 times 1.00 because that's the specific heat of water. Again, if you're dealing with tea, it's probably not that big a deal. If you're dealing with sweet tea, uh, people put a lot of sugar in their tea, and that can significantly change the heat of fusion and heat of vaporization and all that good stuff. So you got to be a little careful about that. But if you're not talking about sweetening it yet, it's probably fine. So in this case, we're going to go from 20 to 0, and obviously the positive figure there would be 20.0. So 20 times 3 is just 60 kcal. So what we figured out was that the total heat required to take out of the ice to bring it down to zero plus to completely melt it is way less than the heat required to bring the tea down to 0 degrees Celsius. So what we know is the tea is going to stay in the liquid state and the ice is going to completely melt. Okay, so the T will be somewhat diluted. Now what we're going to do is use Q loss equals Q gain and calculate exactly how that happens. We can use these figures again, and I will. So I'm going to say Q loss is equal to Q gain. So the thing losing heat obviously is the T. So that's going to be 3.0 times 1.00. Now, in this case, we want it to be positive. We know the final temperature is going to be lower than 20, so we're going to write 20 minus T, okay, where T is the final temperature. Now, that's the only thing that's losing heat. Everything else is gaining heat, which is just the ice, okay? So now we've got to put in the losing of heat for ice and the conversion of it to water. So that's going to have a common mass of 0.50. I'm just going to pull that out in front so we can not have to write the same thing over and over again. So for this case, we're going to first have to bring the ice down to zero. And we know exactly what this multiplication is going to give, but we're bringing the ice down to zero. So that's 0.50 times 10. Again, we got to make sure it's positive. So that's why I just wrote it as 10. So that's the MC delta T, the M being on the outside of the bracket. Now I've got to do the heat of vaporization, the heat of fusion, and we already got the 0.5, so we're just going to multiply it by 79.5. And then the ice has now become water, and it's now going to start changing its temperature. It still has a mass of zero point 0.5. That's why the zero point 0.5 has been out. So we're now going to write 1.00 for the specific heat. And now it's going to go from zero to this new temperature, and this new temperature is higher than zero. So I'm just going to write T there. It's technically T minus zero, but that doesn't matter too much. The good news is we know already what this figure is. This is what it was required to bring the water down to zero. So that's 2.5 kcal. We also know what this part is, the zero point 0.5 times the 79.5. That gives us the 39.85 kcal. So we've got all those figured out. All we really need then is the rest. So if I multiply 3 times 1 times 20, I get 60. So that's going to be 60. Oops, I should probably go back to my purple. So I'm going back to the purple, and I've got 60. And then 3 times 1 times negative t is going to be negative 3t. And then I've got 2.5 plus 39.85. And then I have the zero point 0.5 times 1 times t is going to be plus 0.50 T. So I can get all the T's on one side, and of course the right-hand side will become 3.5 T, but I have to take and subtract the 2.5 and the 39.85 from 60. So if I do 60 minus 2.5 minus 39.85, and then remember it's only good to the ones place, then that's 17.65 kcal, and that's what we have on the left-hand side. I've taken into account the 60, I've taken into account the 2.5, and I've taken into account the 39.85, but the other side is 3.50, and technically I can only have one decimal place on that, and that's times T. And technically the units for the 3.5 in this case is really it was what's multiplied by T, so it's kilocalories. No, it's kilograms times Celsius degrees. So we can go ahead and solve for T by dividing both sides by 3.5, and that gives me T equals 5.04 degrees Celsius, and that 4 is not a significant figure. So that's the final temperature. Anybody have any questions on that one? Now, I did mine in calories because that's the way the numbers that I know, but you're welcome, of course, to do it in joules. That's actually what your author did as well in their example like this. Anybody have any questions on that one? All right. I think I'm going to move along. I'm going to skip 19.8, not because it's not important, not because you're not responsible for it, but just because it's kind of a long, convoluted problem. It's really good for you to learn a complicated problem like that, but it's better for you to actually learn it as opposed to me just showing it to you. So I'm going to leave that one for you to work on yourself, and we're going to go on to the next example because we got other sections to cover here. There is a section called Kinetic Theory of Latent Heats. I really, really, really need you guys to read that. That's true about this whole 17, 18, 19, and 20. There's a huge amount of information that you learn just from reading those chapters, more so than when we get into the electricity and magnetism chapters, even though those are important too. It's just I don't think there's a lot of facts that bear on you every day unless you become a double E electrical engineer or a physicist. I don't think those facts are quite as important. Whereas all this stuff we're learning in chapter 17, 18, 19, and 20 is stuff that every science and every engineer needs to know. So I would really make sure you try to focus on reading all of chapters 17, 18, 19, and 20. And that includes, of course, the kinetic theory of latent heats. That's at the bottom of the page of 549 that I'm looking at right now, or at least the middle of it. So now we're going on to the first law of thermodynamics. This first law of thermodynamics will be a little different if you've had chemistry already. Uh, I'll explain the difference to you. But, anyways, the first law of thermodynamics is about the internal energy. And remember, I told you earlier that the internal energy is the sum of all the different types of energy the molecules or atoms of the substance has. So, if you just take all of a sample of objects, so it could be a chunk of metal, it could be a sample of gas in some kind of container, it could be some liquid or whatever, no matter what it is and no matter what state it's in, it's going to have a bunch of atoms and molecules that make it up. It might be atoms that are made up into molecules, or it might be independent atoms. For instance, if you had helium gas, or if you had water vapor or steam, then you'd have nothing but molecules. But if you take and add up all the different energies that each of those molecules or atoms had, that would be the total internal energy of that object. Okay. Now, as you might suspect, if you add heat to that object, you're going to increase the internal energy. So it might seem reasonable for you if I tell you that the change in internal energy is equal to Q. because Q being positive means heat is being added to the system, and therefore you would get the delta E internal, which is, remember, final minus initial, would be a positive quantity. That means the internal energy is increasing. Of course, the internal energy is going to increase if you add heat to something. Now, here's the other part. The internal energy is actually going to decrease if the object does work on its environment. So if the object or the system that you're studying does work on the environment, then that's going to steal heat from its internal energy. That's going to steal energy from its internal energy. And therefore we write minus W. Now, if you took this in chemistry, if you had this in chemistry, they'd say plus W, because most chemists and most chemistry classes talk about the work done on the substance as opposed to the work done by the substance. So that's the difference. Is you've got to remember that here W is work done by the system. Okay? And Q is heat added to the system. Okay? If the heat's taken away, then it's a negative quantity. So at the end of the day, what you need to understand about the first law of thermodynamics is that it really is a conservation of energy equation. That's all the first law of thermodynamics is. It's just basically conservation of energy. To show you that that's really the case, we could actually go ahead and make this a more complete equation, in which case we would have delta K, the change in kinetic energy, plus delta U, the change in potential energy, plus delta E internal, meaning internal energy, is equal to Q minus W. So those of you who had me for 241, you'll remember that I did something different with my conservation of energy equation. I said something along the lines of K initial plus U initial plus work put into the system is equal to K final plus U final plus E loss plus work out. So you can see now that the E loss and the work out are really just the Q and or the Q minus W. So now it might make a little bit more sense where my original conservation of mechanical energy came from. Okay. But either way, that's not something you have to worry about too much now. Obviously, the 242 course is comprehensive, so anything we solved in 241 is still somewhat fair game for 242, but I usually avoid that. Okay? So we now have the first law of thermodynamics. Let's look at a simple example. Example 19.9. As I said, don't forget to do example 19.8. I just, like I said, I didn't have time to do it, so I want you guys to do it. Using the first law, it says 2,500 joules of heat is added to a system and 1,800 joules of work is done on the system. What is the change in internal energy of the system? So 2,500 joules added to system and 36, or excuse me, 1,800. I don't know where I got the number 36. 1,800 joules of work on the system. Okay, so what that means is Q is equal to 2,500 joules, and that's positive, and W is equal to negative 1,800 joules. And solution, we use delta E internal is equal to Q minus W, which obviously equals 2,500 joules minus negative 1,800 joules. And of course, you can see that's 3,500, which gives you 4,300. So that's the amount of change in internal energy that occurred as a result of these processes. Any questions on that? Pretty straightforward, right? That's supposed to be super, super easy. Example 1910, I'll do this one really quickly. In this one, it says kinetic energy transformed to thermal energy. A 3 gram bullet traveling at 400 meters per second enters a tree and exits the other side with a speed of 200 meters per second. Where did the bullet's lost kinetic energy go, and how much energy was transferred? So that's the big question. What we have is a mass equal to 0.0030 kilograms. In other words, I went ahead and converted the mass of the bullet from grams, which was 3 grams, to kilograms, which is 0.003. We know the initial velocity was 400 meters per second. I'm assuming that's 3 sig figs. And then the final velocity after the tree was 200 meters per second. So the kinetic energy, let's start off with solution. The kinetic energy is given by 1 half mv squared, assuming it's not relativistic, which clearly it's not. Okay. So we can say that the kinetic energy initially is equal to 1 half times 0.0030. I'll leave the units off here, times 400 squared. That's going to give me zero point 0.5 times 0.003 times 400 squared gives me 240 joules. The kinetic energy after the tree is 1 half 0.0030 200. Now, we are making the assumption that none of the bullet's mass, the projectile's mass, changed. There is a good probability that some of it could change. It could hit something in the tree and break loose a little bit. It could be a nail in there, an old piece of fence, or whatever. In this case, we know that the velocity went down by a factor of 2, so the kinetic energy should go down by a factor of 4. That means this is going to be more like 60 joules, but I'll double check my work. Zero point 0.5 times 0.003 times 200 squared gives me 60. So the loss in kinetic energy is around 180 joules. And where that energy went is if you stuck your finger in the hole that was left by the bullet, you'd find it's kind of hot. So some of that energy went into heat to heat up the tree. Other parts of that energy went into work being done on the tree to actually bore a hole in it and to break little pieces of wood and sawdust out so that it all flies out the back end. And some of the work was done in compressing and bending and deforming the bullet itself as well as the little chunks of metal. But the loss in kinetic energy, which is what they're asking for, or the transfer of energy, delta E X for, which means transfer, would be K final minus K initial. In this case, that's 60 joules minus 240 joules, which equals negative 180 joules. And that's the answer to that one. Anybody have any questions on that? All right, so that's some of the simple stuff for the first law of thermodynamics. The rest of the stuff is what I've been warning you guys about with regards to thermodynamics. Thermodynamics is a subject, as well as statistical mechanics, as well as kinetic theory. There's subjects where you have a bunch of vocabulary. So one thing you need to do, and this is true all the time, so you should go back and make sure you do this for chapter 17, 18, 19, 20, is go back and copy down a definition for each of the boldface terms. This isn't necessarily like me asking you about Newton's first law, Newton's second law, Newton's law of gravity, the law of conservation of angular momentum or the law of conservation of linear momentum. I could, in principle, ask you these things, but that's not why I'm telling you this. Why I'm telling you this is if you don't memorize these things, you won't be able to solve physics problems associated with it. So make sure you read that over. I'm just going to use them like you know them. I'll make a quick statement when I need to. But what we're doing here is section 19.7 is thermodynamic processes and the first law. So we're thinking about specific types of processes, changes that can occur thermodynamically, and what that does to the first law of thermodynamics and other things. So first off, we're going to say an isothermal process. So isothermal means the temperature doesn't change. So I'm going to write that as delta T is equal to 0. That also means T equals a constant. Now, one thing we're going to learn a little later in the book than right now, but I'm going to go ahead and show it to you now. We know that work is equal to the integral of F dot dl, which you can write by realizing that pressure is equal to force divided by area, so that force is pressure times area. If you multiply area times the change in length that the area moves through, you get a change in volume. So that becomes the integral of P dV. Okay. Now, something else that we need to know is that in general, for ideal gases, delta E internal, and I'll just subscript this ideal gas. And remember, it's true for an ideal gas, but it's probably going to be very close to being true for all gases, or else ideal gases wouldn't be that useful, right? So delta E is, in some sense, proportional to delta T. Therefore, delta E must equal 0. So that's a big conclusion about isothermal processes. Okay. Now, because of that, because it's isothermal, we can say the ideal gas law is written P V equals nRT. And if you're talking about a constant volume, meaning you're in a closed container, then N, R, and T are now all constants. So you could conclude that work, which is equal to the integral of P dV, is going to become the integral. If I solve this for P, I end up getting N times R times T over V. But remember, N, R, and T are all constants. So I can write N times R times T times dV over V, which equals N times R times T. And now that's going to become the natural log of V final over V initial. So this is another result that we have as a result of isothermal processes. The work is equal to N times R times T times the natural log of V final over V initial. So that's just a couple of the things that we know when a process is isothermal. If we talk about an adiabatic process, that's a new one. An adiabatic process implies Q is equal to 0. No heat is added or lost. Okay? So we don't see much that would do in terms of work equals the integral of P delta V, but we definitely see something that happens with regards to the first law of thermodynamics. Delta E internal, which is Q minus W, all of a sudden has Q equal to 0, so that we have a neat new result. The neat new result is the change in internal energy will be equal to the negative of the work done by the system. And to me, this is really where you really see why work done by the system has to be a negative in there, because obviously, if the system is doing work, it must be losing some energy itself. Hence, you have to have a negative there. Now, one thing we're going to learn in chapter 20, we haven't learned it yet, but the ideal gas law gives us, in addition to PV equals nRT, it gives us P1 V1 over T1 is equal to P2 V2 over T2, or any subset of that. Remember, you could do P1 over T1 equals P2 over T2. You could do V1 over T1 equals V2 over T2, or you could go P1 V1 equals P2 V2. All of those are fair game. But with this, we're going to find out that there's another thing we can use when it's adiabatic, and that other thing is P1 V1 to the gamma power is equal to P2 V2 to the gamma power, where gamma is defined to be the specific heat at constant pressure divided by the specific heat at constant volume. So that's something we're going to learn later as well, but I might as well go ahead and do it now, because chapter 20, what we're going to do is use what we've learned about the ideal gas laws and thermodynamic processes, and we're going to learn about the efficiency of heat engines for different types of heat engines, and then we're going to use the ideal gas laws to derive a formula for the efficiency of a heat engine that doesn't depend on the heat added and the heat taken away, but rather depends on the final and initial temperatures. We can't do that without understanding all these processes. Any questions on that? All right. Now there's another process called isobaric, and that means delta P is equal to zero. It's isobaric. You probably think of it as bars. You've probably heard people talk about a certain number of millibars is the atmospheric pressure. So that's what it comes from. You might want to call it isobaric. That would be certainly fine. But delta P being or being zero, or P equals a constant, does tell us some stuff. For instance, remember, work is equal to the integral of P dV, but that just means it has to be P times delta V. So that's one ramification of an isobaric process, is the work is just P delta V. That also tells us, for instance, that delta E internal from the first law of thermodynamics is equal to Q minus P delta V. So that's another thing we can learn regarding isobaric process. There's another process called isovolumetric or isochoric. These imply delta V equals zero, or V equals a constant. Okay? Since that's the case, we can automatically say that W is equal to zero, because work equals the integral of P delta V, so there's no way you can actually do any work, because the thing is not going to allow it to expand. That's really pretty much the only way you can change it. And of course, that means that delta E internal is just equal to the heat added. So that's some of the ramifications of these various processes, and all that's left in this section, in this next to the last section, is questions about isothermal processes and stuff like that, as well as the next part of the chapter is heat and how it's transferred from one object to another. I think these last two examples, 1911 and 1912, are pretty straightforward. I don't think you're necessarily going to have any trouble figuring them out. And I think I'm going to use our next meeting to do that, but I do want to go ahead and I think you now have a good enough series of examples that you've experienced that you can do all the homework for chapter 19. But that being said, I'm still going to cover a little bit more material next time. But what I'm going to do right now is I'm going to go to the section on, actually, no, maybe I shouldn't. Yeah, I've got a lot more. I forgot that I was thinking this other step was actually what happens in chapter 20, but I realize now that the stuff with the specific heats comes up next. So I don't want to do that now, and I've only got about 5 minutes. So let me work another one of these problems. I just did, the last example I did was 1910. Up there's my alarm reminding me I've got 5 minutes left. Yeah, I can do this 1911. Yeah, here you go. In figure 19.8, we saw the PV diagram for a gas expanding in two ways, isothermally and adiabatically. I'm going to draw that diagram in a second. So the initial volume VA was the same in each case, and the final volumes were VB equals VC, in which process was more work done by the gas. So this is conceptual example 1911. The diagram they're referring to is a PV diagram. And what we have is point A right here and point B right here and point C right here. This line, even though I drew it all curvy, none of them are supposed to be curvy. They're supposed to be fairly smooth like that. But this line is isothermal and this line is adiabatic. Okay. And what they're asking us is in this problem, in this figure, we saw a PV diagram for gas expanding in two ways, isothermally and adiabatically. For a gas expanding in two ways, isothermally and adiabatically, the initial volume VA was the same in each case, and the final volumes were the same, VB equals VC, in which process was more work done. Does anybody know this off the top of your head? I'm going to give you one big hint. There's the big hint. Which one of these processes, going from A to C or going from A to B, which one of these processes is a creates more or does more work? Anybody? Remember we learned A to C. Remember we learned A to B and A to C is the two answers I got. I want to remind you in calculus we not only learned that the derivative was the thing that undoes integrals and integrals undo derivatives, but we also learned that the derivative was what on a graph? Anybody recall? Slope. Very good. And the integral was what on a graph? The area. That's right. So the integral, yeah, it's the area under the curve. So now you can see the area under the curve for the isothermal process is all this area, whereas the area under the curve for the adiabatic process is just this little bit of area. So yes, the answer is more work is done isothermally. And that's it. we'll call it a day. I'm going to go ahead and let you guys split. Make sure you chat me your first and last name if you haven't done so already. I will be waiting for the last person to leave in case anybody has any questions. It's remember it's another office hour, and also don't forget you have your test that's due over the weekend, so make sure you get your first online test done, and also make sure that I can't remember the other thing now. Oh well, just oh yeah, remember that on Thursdays I normally come in and by 5 so that you can ask me any questions in case anybody has them beforehand. So it's like another office hour, especially for you folks that are only meeting me online. So I wanted you to have more time. So by all means, show up. Thank you for coming, everybody. And I will see you next week. Keep an eye on your email. We might be having snow, and I might be sending you out links to videos. Even if we don't miss any school days, I might be doing that just to try to catch us up. So have a good one. Thank you, everybody. Thanks, Nathan.
Mr. Younger,
Yes, ma'am.
I just had a question about the lab because I couldn't make it
Yeah,
yesterday.
I dropped you from class. No, I'm just playing.
Oh, is there any
Yeah,
way I could make that up, or is that I had to be there kind of thing?
no, you can't get the points back for missing, but you can definitely still do the lab report. If you want to, you ended up you're my 242 class, so we actually did a lab. We did a Ohm's law lab, is what it was. There's a way you could possibly do it next week and then piggyback it and do the following lab, or there's a way you could do it virtually. I recommend the way where you don't do it virtually, but you can do it virtually if you want. So I'll make the virtual stuff available for you. Let me actually stop sharing my screen. I'll tell you right now what that is. I'm going to share my computer screen real quick. Oop, I don't want that one. I do want this one. So there's the problem we just worked. I don't want that part though. Let me make sure this is the right course. Nope, that's not the right course. This is the right course. You're in this one right here. So I'm going to take us to this course and show you something that we can do. The lab we did this week was called Ohm's Law. You can see it right here. This is the normal lab, but there are some things we do to make it online. And let me pull those up for you real quick. Just take a couple seconds. So you have time, Anahi?
Yeah, I have time.
Okay. Looking for it, looking for it, looking for it. Lots of files up in here. Okay, I see the Ohm's law. Now I'm looking for the Ohm's law, PHET. Still working on it. Electric fields. No, that's not it. That's not it either. Either way, I'm going to put it up here just as soon as I find it. So if you do need to leave, it's okay. I'm still looking for it and I don't see it yet. And that kind of bothers me. It might be in a different file, but
Okay.
I know I have it around here somewhere because I teach this online as well. So I should have that somewhere around. It's just a matter of locating it. RC circuits, that's not it. That's not it. Faraday's
If
exponential.
not, I could still piggyback it or like.
Yeah, you can still do it. Like just spend a little bit extra time next week on your lab.
Uh-huh.
Uh, Either staying late or coming in early or something like that. You could do Ohm's law first and then do series in parallel.
Okay.
So I'll put this here, and that'll be an option. But you can also do the other option because that stuff is already there. And if you need a little bit more time to turn it in, just let me know, and I can give you a little bit of extension since you missed it. But yeah, I'm not finding the file right now for the PHET, so I'll have to find that later and get back with you. Or
Sounds good.
I won't get back with
I
you, but I'll put
appreciate
it
it.
right here. You're welcome, no problem. Just look for something
Thank
that'll
you.
say addendum, and then it'll have the letters PHET. Okay.
Okay.
All right. Have a good one, Anahi.
Bye.
Bye bye. How about you, Alex? You got any questions?
I have one question on example 19.7. I was hoping that you could explain one part to me. And that was whenever
Okay.
we were
It was one of the
uh
ones that I did.
yes.
Okay. Let's see if I can find what that was.
I wrote it down and then I didn't write down what it was. but
Gotcha. All right. Well, that means I'm probably going to pull my iPad back out, so I'll do that real quick because you're going to need to see that work anyways. 1997, there it is. Okay. I know which one we're talking about now. Now I'll stop sharing here, and I'm going to start sharing here. All right, it's coming up any second now. So there's example 19.7 at the bottom half. What part are you confused about or questioning?
so around here, can you see
Mm-hmm.
that on the screen?
Yes.
All right. So I understood what these three represented,
Uh-huh.
QI, but I was just confused on what was circled right here.
Okay, so
Is that
these two over here, this is M, C, delta T, but that's
um
for the ice. Notice the C is point 0.5. So that's the ice in going from -10 to 0. And I had to put it in the opposite order so it come out positive. This is zero point 0.5, the mass, times the latent heat of fusion, 79.7. Actually, I wrote 79.5, but it's supposed to be 79.7. I'm wondering if that might be a mistake, but I still got it right, so not a problem. And then this one, zero point 0.5 times 1 times T minus 0, that's after the ice has melted and has become water. So now it has a specific heat of 1, and it's going to change temperatures from 0 degrees Celsius, which is what it was when it turned from ice to water, up to this new temperature T. So that's why that term's in there.
okay? Okay, that makes sense.
Does that make sense?
Ooh,
Yeah,
yeah,
it's
I'm just
kind of tricky and it's easy to leave that part out, but yeah, you got to remember, hey, once it becomes water, I got to deal with it as water now.
I'm
That cool?
definitely wrapping my head around this part, the Q equals ML,
Hmm.
and when to use it. Because yeah, I would definitely forget to write this down, if
Yeah,
anything.
that is on our equation sheet at least, so you at least have that. But it's something you got to keep in your mind when you're solving a problem. You just got to remember, hey, is it changing state? Because if it's changing state, we're gonna have to use a latent heat as well.
Cool. Well,
All
thank
right,
you for that clear up.
no problem. Have a good one, Alex. Let me know if I can do anything else for you.
Oh, I got to figure out how to get out of this pen thing because I can't do that.
Yeah, I was
All
impressed
right.
that you were able to write on my screen. I hadn't figured out how to do that myself yet.
Okay,
All
well,
right,
I'll see you next Tuesday.
have a good one. Stay safe in the weekend.
You too.